preserving congruence. Congruence just talks about, it just means, congruent means same size, same shape. It keeps the same size, same shape. We're going to mostly talk about it referring to the size. That's what you need to think about. And the word preserve just kind of means keep. Is it going to stay that size or is it going to change? Okay, so the first part of this is true false, which are really tricky the way they word them. But dilations are the change in size of a shape. Either a shape is getting smaller or a shape is getting larger. So if this sentence says a dilation may not always preserve or always keep congruence. So basically it's saying a dilation may not always keep the same size. Is that true or is that false? So not is the key word in that. And that would be true. A dilation may not always keep the same size, and that's true because that's what a dilation is. That's when the size is going to change, unless the scale factor is 1, which it rarely is. So it's always going to change. Yikes. True or false? A reflection, a flip across the y-axis may not always preserve congruence. So when we flip something across any axis, it doesn't matter. If we flip something around, the size is not going to change. So this is going to be false because it's saying a reflection may not always keep the same size. That's not true. If we flip it, no matter where we flip it, it's going to stay the same size. A rotation or a turn, doesn't matter how, will always preserve congruence. And that's true. That's just like the reflection. Just because we turn something doesn't mean the size changed. It just changed the way it was facing. A translation, a slide, doesn't matter how, will always preserve congruence. That's just like the other ones. The only one that doesn't preserve congruence or keep congruence, keep the same size, is dilation. So that is true. Number 5, a flip across the y-axis will always preserve congruence. Again, that's true. A rotation, a turn, may not always preserve congruence. So basically it's saying a turn of a shape will not keep the same size. That is false. A translation or a slide may not always keep the same size or preserve congruence. That is false. Write the new coordinates if they are moved 7 units to the right and 3 units down. Coach Elkins kind of gave this in class. He kind of wrote most of these down. But the going to the right is the x-axis, and if we go to the right, those are our positive numbers. So we would be adding that 7. That's what we're doing with that 7. We're going to add it to all of the x values. So I'm going to say plus 7, plus 7, plus 7. Then on the 3 units down, if we're going down, if we go up or down, that's talking about the y-axis. And if we go down, that means that's all of your negative numbers. So on that one, I'm going to switch colors. That would be subtracting from all of the y values. So minus 3, minus 3, minus 3. And then you're just solving it. So negative 4 plus 7. Negative 4 plus 7 is 3. Negative 5 minus 3. Don't do minus negative, just do minus 3. That's negative 8. Y, negative 5 plus 7 is 2. Negative 9 minus 3, just minus 3. Negative 12. Z, negative 6 plus 7 is 1. And negative 11 minus 3 is negative 14. And that's all you're doing on those. So 2 units to the left. Okay, so if you go to the left, that's your negative numbers on a coordinate plane. So that would be minus 2. And if we go up on the y-axis, that would be your positive number, so adding 8. So minus 2 from each x value and plus 8, if I can squeeze that in there, to all your y values. Same thing on number 10, but they switched them around. So if we're going down, that's talking about the y, that's the second number in your coordinates. And if we go down, that's our negative numbers, so minus 5. So on all of these, the second number is being subtracted by 5. And if we go to the right, that's our x-axis, and those are the positive numbers, so plus 11. So plus 11. And same thing on number 11, they flipped them around. So 1 unit up, that's plus 1. 5 units to the left, that's minus 5. But that's my x, that's my y. They flipped them around. So I'm going to add 1 to each y value, because remember coordinates are always x and then y. And I'm going to subtract 5 from every x value. Minus 5, minus 5, minus 5. So you're just solving those, getting new coordinates, and that's all you're doing. That is your answer, just writing the new coordinate. Same thing on number 12, 8 units to the left, that's minus 8, and 7 units down, that's minus 7. On these, we're doing, on 13 through 16, it's just yes or no, or y or n. 13, if a shape is dilated, that means the size change. And it doesn't really matter what the scale factor is for this part. It's just asking if the orientation, so that's the direction a shape is facing, and or the congruence change, the size. So when we dilate a shape, it's just saying it gets smaller or it gets bigger. So the direction it's facing will not change. No. But the congruence does change. Dilation is the only one where the congruence changes, so yes. If a shape is reflected, it's flipped. Does the orientation change? And does the congruence change? If it's flipped, the size does not change. And if a shape is rotated, same thing. If it's turned, if you turn yourself around, you're going to be facing a different way, but you're not going to get bigger or smaller. And if something is slid, if something's translated, if we slide something, the orientation doesn't change because we don't turn anything. That's the only weird thing about the translation. You're not turning it, so there's no reason the orientation should change, and the size is not going to change. 17, y'all haven't done this quite yet, but the algebraic representation, if a shape is translated 8 units down, that's your y, and 2 units to the left, that's talking about your x. So that would look like, if you were to write an algebraic representation of it, remember for coordinates, x always comes first, right? It's x and then y. So you have to write what's happening to the x value first. So if the x value is being moved 2 units to the left, and I know that on a coordinate plane, going to the left are my negative numbers, going to the right are my positives, up are positives, and down are negatives. So if it's moving to the left, then that means it's being subtracted or negative. So we would write x minus 2. And then the y, what's happening to the y, it says it's going down. So it's going down, those are also negatives or minus. So I would write y minus however many units, it's at 8. And that's it. That is the algebraic representation. It just sounds fancier than it is. It's not really that fancy. The same thing on number 18, the algebraic representation if a shape is translated 5 units to the right and 11 units up. So think about what's happening to the x value first, because x always comes first. It's translated 5 units to the right. So if I'm going to the right, those are my positive numbers. So plus 5. And then what's happening to the y, or am I going up? Those are my positive numbers too. So that means I'm saying plus 11. Number 19, if a shape is dilated by a scale factor of 4.5, what happens to the side links? The scale factor is larger than 1, so it's going to get bigger. If a shape is dilated by a scale factor of 9, what's going to happen to its angles? Nothing. Because if we have a 90-degree angle, say we have a 90-degree, a right triangle, that's what I'm trying to say, and there's a 90-degree corner, because that's what a right triangle is. And then say we dilate it and we make it teeny right here. Okay? We dilated it, but we just dilated. We just changed the side lengths and we made them way tiny. It's still a 90-degree, well, kind of. I just can't draw. It's still a 90-degree angle. So the angles, regardless of the scale factor, will never change. The angles will stay the same. Those degrees stay the same. Same.